All right. Well, welcome to the final CC Colloquium of 2021. We're very pleased to have an in-person speaker who will be introduced momentarily, and it's cool to see. We got about twice as many people here in the theater as we normally do, so that's awesome. So first of all, some announcements. These are all public outreach and community announcements of various sorts. So first of all, Virtual Night Sky is tonight. It's the last one for the semester. You can find details about that in your email somewhere. And they will be featuring the top 10 things to look forward to in 2022 in the night sky, I presume. That's number one. Announcement number two, CC Community Conversation with CC Leadership is tomorrow at noon. Again, there should be an email that should have a URL for Zoom link for that. And then finally, looking ahead into 2022, ASU Open Door, the big public outreach event, which is in February, I believe. Is that right? February 26th. If you are interested in participating as an exhibitor, please see the survey that went out in email today and complete that so that Kim Baptista can start to figure out who from CC is going to be involved in that. And I think the deadline for that is pretty soon, right? December 6th. Please respond by December 6th so that we can start to organize Open Door, which is February 26th. And it will be in person. So it'll be a big in-person outreach event. And so they definitely want to know who's going to be there to try to organize it safely. So with that, I'm happy to turn this over to Jim Bell to introduce our speaker.
Thank you, Ariel. Hey, everybody. Welcome to Colloquium. We're in for a real treat today. It's a real pleasure to introduce Dr. Gordon Osinski. He goes by Oz, even to total strangers, I'm told, right? Great to have him here. He's a professor from University of Western Ontario. I want to get this right. The Industrial Research Chair in Earth and Space Exploration in the Department of Earth Sciences, and also the director of the Institute of Earth and Space Exploration. You're here in the School of Earth and Space Exploration, so great name choice. He also directs the Canadian Lunar Research Network. So his research focuses on impact processes. You'll hear a lot about that, the geology of impact structures on Earth, Moon, and other planets, glacial, paraglacial landforms in the Canadian Arctic, and analog environments on Mars, impact melt-bearing meteorites, asteroid and lunar origin and evolution, and origin and evolution of life on Earth and the search for life elsewhere. So here, this talk, Oz will be combining two of his research passions having to do with impacts and astrobiology. So that's pretty exciting. Oz is also a co-eye on the PanCam instrument on the ESA ExoMars mission launching next year. Very exciting mission for ESA, and also is involved in providing training to Canadian and US astronauts as part of the NASA Artemis human lunar exploration program. Oz is also here working with a number of us this week on ASU's Milo Space Science Institute. Canada has become a member, and we're working on some great project ideas for workforce development and actual flight projects to the moon and beyond. So Oz, welcome to ASU, welcome to CC. We're really looking forward to your talk today.
All right, and thank you, everybody. Thanks, Ariel and Jim, for the introductions, and it's a real pleasure to be here today. I helped create the Institute for Earth and Space Exploration about 2 or 3 years ago, and definitely, ASU's School of Earth and Space Exploration is definitely something that we look to emulate, and it's been a great meeting many of you this morning, and I'm around tomorrow as well, and look forward to meeting with many more of you. So yeah, it's kind of my pleasure to talk about what's become one of my favorite topics and kind of major research themes is looking at meteorite impacts through a different perspective, that of the beneficial effects of meteorite impacts, their potential role in the origin of life. And so it was actually Ariel who nudged me to come up with this title. There's a question mark at the end, but I'm going to talk about a potential cataclysmic origin of life. I would like to say a special thanks to 3 people who have really been with me on this journey looking at the astrobiological potential of impacts for a long time. Charlie Cockell from the University of Edinburgh, who's prominent in the UK astrobiology scene, and then Alex Pontefract and Haley Sapers, 2 former PhD students who've gone on to do great things. Okay, so I think most of you in this room are probably familiar with what this is, the solar system. But just to kind of get us grounded, I like this particular version because it, emphasizes the fact that, there's a lot of material left over from the building and creation of our solar system. We've got a nice comet coming in. I think my laser pointer is not going to work here. But anyway, a cometary object coming in, and of course, all of the asteroids there. And so, the moon is a witness plate to solar system evolution and to the impact history of, what has happened in our neck of the woods here in the inner solar system. You don't even need a telescope on a clear night and a full moon to look up and see that, impact cratering, the impact of asteroids or comets with planetary objects is ubiquitous. It's happened since, day one, time zero in the creation of our solar system. And as far as we know, is going to probably outlast all of us and the Earth and everything else in our solar system. The moon also is a reminder that, because of its proximity to the Earth, what happens on the moon happens to the Earth. And if our planet wasn't so geologically active, as it were, we would have fared much worse than the moon and have many more than the 30, 50 or so thousand impact craters on its surface. So when we do, when we think about meteorite impacts, if I give a public talk, if I was to poll even most of you in this room, maybe ask you the first thing that pops into your head if you think about a 20-kilometer object hurtling towards Earth at 15 kilometers a second. The first thing is probably not a very positive thought, right? Some combination of expletives and thinking about the end of the world and mass extinctions. Of course, I think there's been some controversies over the decades, but the more we learn, the more I think we understand that 66 million years ago, an asteroid struck what is now the Yucatan Peninsula in Mexico and caused the last big mass extinction on Earth. And it's a good it's a good reaction to have, is to think about the destructive effects of impacts. This is a famous plot in Bevan French's book, Traces of Catastrophe, that on the y-axis is essentially how frequently events occur, and on the x-axis is the energy, and quite a bizarre unit, but tons of TNT equivalent, and this is in megatons. And that comes from really a lot of what we know about the destructive effects of impacts, and the energies involved comes from the very well instrumented nuclear tests of the 1960s and 70s. And so, even Meteor Crater that was on the first screen that I'm sure all of you have, or if you're a new student, hopefully will do, as COVID allows, get up to see Meteor Crater just a couple of hours up the road. 10 to the 1-ish megatons of TNT equivalent. It's already a couple of orders of magnitude more energetic, more powerful than the two atomic bombs that brought World War II to a close. And then the numbers, even to me, start to get a bit meaningless when you start to think of Chicxulub, 180 kilometers diameter, right down the bottom right of the screen there. 10 to the 7 ish megatons of TNT. And so, impact events are really unlike any other geological process. Not only do you have that huge energy, but it's released almost instantaneously and at, essentially a single point on the Earth's surface. It is not distributed over a very big region. So in thinking about life, if we move from, recent-ish mass extinctions to the origin of life, this led to a lot of ideas that either impacts, annihilated ecosystems or caused the frustration of life early in the solar system's history. This is a great plot that Nicole Zellner put together. A lot of debate, and I know there's people in the room who are looking at this in terms of, we don't know exactly what happened with the impact rate in that first 500 million years. We do know that it was high early on, and then eventually kind of came down to the steady state that we know of today. Whether it was a fairly rapid drop and then a cataclysm or a late heavy bombardment, sawtooth decline. Regardless of that, we know in the first billion years or so of Earth's history, And actually more recent studies, from modeling would have that go into, 3.5, even down to 3 billion years. We think that cratering rates on Earth were, 1 or 2 orders of magnitude higher than they were today. So if we kind of explore, the origin of life a little bit more, of course, this is happening in the Haitian period. Hades, after the Greek god of the underworld, god of death. We weren't around, nobody was, and there's really no rock record to speak of. So, if you Google the Haitian period and choose images, you'll have lots of artist reconstructions and, volcanism, lots of volcanisms, a very fiery planet, and, lots of asteroids and things are hitting the Earth too. And again, we know from the lunar impact record that, potentially 10 to 20 times more impacts than there were today. At the same time, and kind of the counter is that we're continually pushing back the record for early life on Earth. It becomes more controversial the further back we go, often because of how metamorphosed the rocks are, and even actually how old the rocks are. This, in the last few years, there's been some controversial potential, biosignatures evidence for life in very ancient rocks up in Canada. And the date of those rocks is the more controversial thing, not necessarily the biosignature. But if that kind of stands true, then, we're pushing life back into the Haitian period. And so, we got to kind of ask ourselves the question, and it's something I've been asking myself for a long time, how and why even did life arrive at this most inhospitable time in Earth's history? And so I want to offer a hypothesis, which is that, impact craters were not only the destructive, effect that we think about, but that they created conditions suitable for the emergence of life through the production of substrates, the delivery of life essential elements, the building blocks for life, and through the production of habitats for life. And so I'm going to focus on this for, the rest of the talk today. This would be probably 2 or 3 hours if I covered all of these in detail. So I'll focus a bit more on the habitats for life, which is something that, I've been focusing on in my group for the last couple of decades or so. And my approach has been, my background is in geology, both as an undergrad and a PhD student. And so taking a look at the terrestrial impact record, this image of the Earth is probably the worst one to use for, trying to understand the impact record. It looks nothing like the moon. You'd be hard pushed to spot a single impact feature. But we do now have about 200 or so confirmed impact craters on Earth. I just generated this last week. So this is kind of an up-to-date view of hypervelocity impact craters, smaller impact craters without evidence for shock, and then impact deposits, so spherical layers and tektite fields too. And I'll do a shameless plug for a website, impactearth.com, which is a kind of database of terrestrial impacts on Earth. And if you want to learn more, definitely make your way there. Actually, I think this is a screenshot for that. And so, as part of this, this gives us a bit of an insight into, 200 craters. It's nothing like the record on the moon, but we're at least able to go and study them, collect samples, bring them back to labs, and learn more about, the post-impact effects of impact events. Okay, so when I mean habitats, this is a habitat for microbial life, and the key thing here is that this habitat wouldn't have existed without the impact event. So it either didn't exist beforehand, or it was generated primarily because you had an impact crater. Kind of 4 main aspects, and again, I won't go through them all. Probably the most familiar, especially to a lot of the Mars folks in this room, is the idea of impact-generated crater lakes. Most of the lakes or evidence for lakes we see on Mars are in meteorite impact craters. And the last couple of big missions that are still active with Curiosity and now Perseverance are exploring crater lake environments. But I'm actually not going to talk about that one. I will touch on the other 3. And I'll begin first with impact-generated hydrothermal systems. And already I've had some great discussions, some thought-provoking ones earlier today on this topic. So hydrothermal systems, for those of you not familiar, comes from two Greek words for heat and water. Essentially, most of the active hydrothermal systems on Earth today are in volcanically active regions where we have, magma, volcanic rocks as the heat source. You essentially have a heat source plus water. You can generate a water-rock interaction, through convection. We can have discharging of fluids at the surface, either as liquid or as steam. And we know from lots of studies, including from people in this room, hydrothermal environments are, really area habitats that a lot of people think that life may have originated on Earth for a number of reasons that we can go into later. So over the last couple of decades, we've been building up, and really when I started my PhD, I came from the UK to Canada in '99, there's a few people that published on it. Horton Newsom from New Mexico had published a few papers, but there wasn't really a realization or connection between impacts and hydrothermal systems. But I think that's definitely changed over the last couple of decades. Although I was telling the students over lunch, there's still not many people working on this topic. So if you got questions at the end, there'll be a number that I can't answer because we just don't have the answers yet. So this was a review paper that Mikhail Naumov did a couple of decades ago of what was then known of impacts and where alteration occurred. And so the kind of solid black dots are 20 years ago, where evidence for hydrothermal alteration had been found in an impact crater. I would put a lot of money on that most of the open circles where evidence hasn't been found is mostly because people haven't looked. The rocks are maybe buried or just not accessible. Although there is a size cutoff. Meteor crater, someone asked me at lunch, we really don't see any evidence for hydrothermal alteration there. So there is at some point a size threshold where you don't have enough heat and you don't likely have enough water to generate hydrothermal systems. But even that, where is the cutoff in terms of crater size is one we don't have a good answer for right now. So these are all sites that I've been looking at over the last little while, and I could give a talk just on hydrothermal systems. So I'll delve into and take you up to the Canadian Arctic. This is where my career began in meteorite impacts, and where I keep going back to both in the field and in the lab. They're really one of the world's unique impact craters. This is the Horton impact structure. You're looking at a Landsat, probably 7 or even older image, which is about 30 kilometers across, more or less true color. So Horton is about 23 kilometers across. So on Earth, we put that in kind of a mid-sized crater category, and formed about 30 or so million years ago, so relatively young geologically. The nice thing about Horton is that virtually nothing has happened to this region since the impact 30 million years ago. As I was again discussing with the students over lunch, we use this as an analog for Mars too, because it's a polar desert environment. Even glaciation up there was mostly cold-based. And so, there's been relatively little erosion. The rim is out here. There's been, some subduing of the rim, but we have a little bit of ejector preserved here. And in the crater interior, those gray rocks are not snow. To get your eye in the top right, there's some ice-covered lakes and a bit of snow around. But the grayish material in the center is what we call the crater fill impact melt rocks, or impact melt sheet. So these are rocks that were melted by the impact. And to get into hydrothermal systems, that's one of the major heat sources, is that the energy deposited by an impact can melt, many cubic kilometers of rock, generating one of the major heat sources for a hydrothermal system. The other heat source comes from rocks uplifted from depth. If any of you have studied impact craters or looked at larger impact craters, so not your simple crater like a meteor crater, but in larger craters, we get uplift of rocks from depth in the crater interior. At Horton, that uplift was only maybe a couple of kilometers, and so that's not going to contribute much to the hydrothermal system. But if we go up to Sudbury in Ontario, a 200-kilometer diameter crater, rocks in the central uplift of that crater would have come from 20 or even 30 kilometers down, instantaneously. So they were quite hot down there, and that's another major heat source for these larger basin size impacts. So, if you're a field geologist, this is a fantastic place to do field work. Everything's there. There's no vegetation, polar desert environment. And if any of you have done work in northern Canada, there's not even any bugs here. We're too far north for any bugs. So it's just a great place. You've got to occasionally deal with some inclement weather, even in the middle of July, like this. And actually, this is what it was like when I left yesterday morning from London, Ontario. So I've also been enjoying that aspect of visiting Tempe here too. But some other challenges come in the form of the occasional polar bear ripping into your kitchen tent, and so there's some, coming from the UK where we don't have any guns, being hanged at a shotgun, to go out and do field work was still probably one of my most memorable moments from my first field season at Horton. Okay, so one of the things that I started out for my PhD was mapping this crater. It hadn't been done before, and so over the course of a few field seasons, we're talking about a couple 100 square kilometer area. We were able to generate a good geological map of this crater, which we actually have very few of for any impact craters on Earth. So this is very simplified, but it highlights kind of the hydrothermal system and the main components of that. So in the crater interior, the orange is those impact melt rocks. So that's the main heat source. In this, lilac purplish color, that's the central uplift. So rocks that are being uplifted depth. And then all of the red dots are basically hydrothermal deposits that I mapped in the field. And hopefully one of the first take-home messages, and I like to talk about this when thinking about Mars exploration, is that it's not a random distribution. Hydrothermal alteration is concentrated into a few key distinct zones around meteorite impacts, and we'll get into that in a second. So what is the evidence? Well, if we start first off with alteration in these crater fill melt rocks, there's a rock hammer there for scale. And this is one of the nicest examples, one of the biggest. We call this a vug. So, it's a big cavity essentially lined with hydrothermal mineralization. So these are the melt rocks. If you've got good eyes, again, I don't think it shows up. There's a big clast up here. So this is kind of a melt-rich breccia. The greenish sparkling material is marcasite, that's iron sulfide. And then we have a lot of carbonates, calcite, sulfates, and sulfite minerals dominating the system. For the Mars folks, there's also a really neat, actually present day ongoing weathering story, because this yellow popcorn-like material in the center is actually mostly jarosite. And so there's some, interesting alteration of sulfides going on in this fairly, dry, cold environment too. We see nice, lots of gypsum. And so, as a quick aside, because I don't have another slide later on, the mineralogy of impact-generated hydrothermal systems, unlike, most more magmatic ones, is really dominated or driven by the target rocks that you hit. So the target rocks for this particular crater were predominantly carbonates and evaporites overlying a Precambrian crystalline basement. And so, the hydrothermal minerals, not surprisingly, because that's where you got the elements from, typically carbonates, sulfates and sulfides. With Mars in mind, if you go to more silicate target rocks on Earth, they're typically more clays and zeolites. So just to kind of note that here. But the settings and the style of mineralization is the same depending on the target. Of course, the other really unique thing about meteorite impacts that is good for hydrothermal systems is that you need a path to get the fluid from point A to point B. And I haven't got into kind of cratering 101, how impact craters form, but you again deposit a huge amount of energy in a single point in the Earth's crust, and you heavily fracture and fault, a very focused, localized region. It's the reason that a bunch of very prolific oil producers in the Dakotas and in Oklahoma are in meteorite impacts as well. They make really great reservoirs because you fracture the rock and then put a cap on top, and you've got a good hydrocarbon reservoir too. But it also means you've got a big fracture network for fluids to be transported and to set up convection in these impact craters. And so this is an example for around the edge of the central uplift, where the rocks are quite heavily fractured and busted up, and we've got some veins here of calcite. One set on the screen, and then another set going on near the Swiss Army knife there. One of the things that is maybe slightly not as interesting to look at in the field, but which I think is one of the most important things astrobiologically, is what I started out mapping as pipe structures. And so these are these kind of two orange kind of vertical-ish structures here that are on the slope in front of you. When you go to them, these are heavily brecciated, a few meters across. And when we kind of look, with analogy at modern active hydrothermal springs, we essentially think these are the conduits that, maybe just above the screen here would have been your hot springs and or steam vents. And so these are these structures that actually interestingly occur mostly around the crater rim, and that we interpret as fossil hydrothermal vents. As I was joking to a few people, it's one of the drawbacks of looking at meteorite impacts from any perspective, understanding how they form is, it's good for human society that we haven't had a recent big one, but it does mean that, unlike volcanic systems, we cannot go there and witness, an active impact hydrothermal system. We can't witness a crater forming, and so, we're left looking at the products, doing experiments or numerical modeling to get at the process. Okay, so I just actually threw a couple more slides in for another crater because it's quite interesting, because this came up at lunch. Is there a common kind of template, or do you see similarities with craters? So the answer is no and yes, but even for craters of the same size. And so this, some of you may have been to, is not the Arctic anymore. This is the Reese crater in southern Germany, another really unique well-known impact crater that's been studied for many decades. The drawback is that it's wooded and lots of fields, so there's not a lot of outcrop, but there are some key quarries where you can go and look at some of these outcrops in 3 dimensions. And the added benefit at the Reese is that while the crater interior, there's no access to the crater fill melt rocks, on the surface there is drill core. So we also get a bit of the 3-dimensional perspective at the Reese that we don't have at Horton. And just in one slide to summarize it, and kind of shown schematically in the top left there, we see at the Reese, especially in the crater interior, a lot more pervasive hydrothermal alteration. So at Horton, you can walk around and pick up, bits of impact glass that formed 30 million years ago, and they're absolutely pristine, not a speck of alteration. So the hydrothermal alteration at Horton I would characterize, as restricted to cavities and vein networks and things, whereas at the Reese, in the crater interior, it's kind of shown in this progressive alteration scale on the right of these glass-bearing breccias. There's not a single bit of glass preserved in the crater interior. It's all altered to clays and zeolites. And so there was a more active, more pervasive hydrothermal system at the Reese. Why? Same size crater. So, you would think, that the system should last about the same duration. I think, or the only explanation I can come up with is that at the Reese, we had a very rapid formation of a crater lake. And so I think it was a combination of having that crater lake there, a lot of fluid flow going on, immediately after the crater formed, whereas at Horton, there's less evidence that we had that, at least a crater-wide crater lake forming. And so, this is something I've been thinking about for Mars, and that I think we need to look at a bit more detail. So kind of pulling this hydrothermal story together, This is a schematic cross section, but it's really actually based on Horton and the Reese primarily, or where in an impact crater you will get hydrothermal deposits. And so I've kind of identified here 6 main locations. We have, number 1, the crater interior, and this is probably, I think, in 1980, Horton Newsom published on this, including a paper on Mars about, impact melt rocks being hydrothermally altered. And so that's been something that's been known about for a while. From our studies at Horton and other craters, definitely the alteration is concentrated towards the base. And so you can think of, an impact hydrothermal system with that, even though they're altered, that crater fill lens, an impact melt sheet acts as a bit of a cap. And so it concentrates fluid flow towards the base, towards the interior of the central uplift, and then towards the crater periphery. From drilling the Reese and other craters, we know that you can get increased alteration, both kind of inwards and downwards in central uplifts. At Horton, we discovered a really intense kind of zone of alteration that since been kind of looked at a few other craters in this, quite chaotic zone where you have the crater rim collapsing inwards and the central uplift collapsing outwards during the final stages of crater formation. And, the rocks there are the most fractured in the crater. And so we get that, third kind of setting. The fourth setting is a really interesting one, in particular for Mars, I think, is impact ejector deposits. And, at the Reese, even though the ejector deposits are only 20 or 30 meters thick, there's hydrothermal alteration in them. And, for Mars, where if you scale it to basin size impacts, you can distribute ejector potentially over the whole planet, but at least, regionally hundreds of meters thick. If we think about, cratering in the first half a billion years of our planet's history and Mars's history too. Again, I think one of the most interesting settings, if I need to mess a bit more, astrobiologically, are these hot spring environments that we definitely think, or from what we see at Horton, those pipe structures are really concentrated around the crater rim. And it does make sense because that's where you have, the really major faults occurring. As the crater collapses inward, this terrace crater rim region is where you have, kilometer scale faults and a lot of opportunity for fluids to be transported. A less well studied one is, lost my mouse, is location 6. And this is where I've got a student doing some ongoing work at the Reese. Is this, the idea that you can actually get alteration occurring of the basal lake sediments. And so at the Reese, it definitely seems to be the case that, you had the lake form very quickly, sediment deposition happening, and the hydrothermal system was still active then. And so you've got alteration of those basal lake sediments. And so, not only do you have that quiescent lake environment, which on its own is, interesting astrobiologically, you can have hydrothermal venting into that situation too. So this is something, some ongoing studies at the Reese, and Gernot Arp has published on a couple of really interesting locations in the Reese where he thinks you have essentially spring mounds at the base of that crater lake environment. Okay, so kind of temporarily, that's something that will eventually dissipate. The hydrothermal heat source will eventually cool down, and the hydrothermal system at some point will stop. But there are other habitats that, are actually still around at the present day. And this first one is, the impact processing of crystalline rocks. So what do I mean by that? Well, if you study impacts, it deposit a lot of energy. Between 0 and then melting the rocks, we get what's called shock metamorphism. And so you're changing the rocks, the properties of the rocks, sometimes their mineralogy, but definitely their physical properties in the solid state. And it turns out you get a colonization of these rocks by endolithic microorganisms. So endolithic means within rock, endo within and lithic rock. This is not from a crater, but this is where endoliths were first really recognized, was in sandstones from the dry valleys of Antarctica. And we essentially have, if you go to the dry valleys, just like at Horton, and you wander around, at first glance, it's like there's no life here. This is lifeless, just like the surface of Mars. So, but you crack a rock open, and that's what's shown, in the screen here. Life is living within the rock, and it's doing that because it's offered protection from UV, a protection from really quite big temperature swings, and it's a moisture retentive environment, which of course to more extremes is also what we have on the surface of Mars. And so this was something that we discovered early on at Horton, some early publications from Charles Coquelle, and then some later work by Alex Pontefract. Is on the right hand side. It's not as kind of bright and extravagant as this sandstone, but I think it's even more relevant for planetary science nonetheless. You'll see a little layer of pink and of green in that particular rock. So people have now studied endoliths from around the world. They are, 99.9% of the settings are in sedimentary rocks, for two main reasons. One, you have porosity in sedimentary rocks, and the other is that, in minerals like quartz, sunlight can penetrate, to a few millimeters, so that photosynthetic cyanobacteria can use the sun's rays for energy. This rock on the right is actually a lump of the Canadian Shield. This is a 3 billion-year-old lump of gneiss, where endoliths would usually not have any chance of getting in. And so what has happened, solely because of the impact, is that you've increased the porosity and actually, interestingly, the translucence that allows a greater penetration of light and allows, endolithic colonization of the rock before the impact would not have been colonizable. Kind of show you a bit more visually of what's going on. This is a plot from one of Alex's papers. She did some experiments where we took these rocks shocked to various different scales. If you've taken any classes with Tom Sharp, you probably talk about different shock levels. Essentially unshocked stage 0, and stage 7 on this scale is almost melted. So we took rocks of various different shock levels, sterilized them, and then she did culturing experiments. And so you'll see a pretty nice correlation with increased colonization of cells with increasing shock level. And if you look at some backscattered secondary electron images from the scanning electron microscope, each of these images is maybe half a centimeter across, and this is what a gneiss should look like. There's virtually no porosity. There's a couple of teeny little fractures, but that's what a chunk of gneiss or volcanic rock should look like. As you come up to kind of mid-shock levels, you're increasing a lot of fracturing, and that keeps going up. And then when you get up to the high shock states, the rocks are almost pumice-like. The best analogy here is that these highly shocked rocks, kind of on the point of complete melting, have really high porosity and permeability, and these kind of network of fasciculated glass. And so these are in gneisses. Again, actually, here is where I have a couple of students working on shocked basalts, from a couple of craters in Brazil, to see if this holds for increasing shock level in the basaltic targets too, which is of course more relevant. I think the early results, not to give away my student's thesis, is that it's a similar trend with increasing shock level. You're increasing the fracturing, porosity, and the permeability of a basaltic rocks too. If we go one step further and we melt the rocks, we actually have glassings, and this is also a unique habitat. One of the things actually I found during my PhD, and this is one of those fun kind of things that happens in science, is that I distinctly remember it before Neil Banerjee and I, we were at Early Mars Conference 2004, before he and I were profs actually, and we both ended up at Western. Neil actually started working on volcanic glasses, where they found these quite unique tubular features. And he presented on that. And I remember sitting there in a room like this, looking at it like, holy, I see, I've just seen something like that in glasses in the Reese crater that I was just finishing up my PhD on. You know, parked that thought for a while and then came back and we both ended up at Western. And so on the, I always have to get this right because they're so similar, but on the top is essentially, you know, there's now an extensive literature on the bioalteration of volcanic glasses. And essentially these, you know, you can think of them as trace fossils. These are essentially borings in glass that were made by microbes that are no longer there. So trace fossils. You see this beautiful, you know, segmentation of these features. You see bifurcation in, you know, B and F. Both of these, you know, are really hard to do abiotically, but it's something that life does. They can be hollow as well in kind of C and G and onto D and H. And so, you know, coming back to this previous point, this is probably one of the most favorite images in the bottom left here. This is a whole bunch of, it's something like 300 images from an optical microscope stacked together. So you're seeing a bit of depth. And, you know, you see, if you look closely, you know, some of these features are spiraling into the screen, this segmented texture. And so, you know, they're not quenched crystallites, which form and melt as you rapidly quench it. But we think of these, you know, essentially bioalteration features of glass. And so it's now found to be fairly common in volcanic rocks in submarine environments. And, you know, we found this in glasses in the Reese crater in Germany. And so again, you know, the neat thing about this is that, you know, impacts anywhere, everywhere on any planetary object are going to generate a glass and melt material. Now we do time. Okay. So I'm not going to talk about this too much. You know, this is really drawn from the literature, and you know, there's a lot of folks in the room who study, you know, carbonaceous chondrites. But this is getting, you know, to also the delivery of material from impacts. You know, even in large impacts, some material can survive. Of course, in smaller, you know, when smaller chunks of rock are hitting the earth and land as meteorites, of course, most of that survives. And, you know, this has been known, you know, for a long time, work that Schreiber and Sagan did in the 90s, you know, quite a few different ways of delivering organics and other life essential elements through carbonaceous chondrites. And, you know, the more we learn, I think the more we're finding that they're chock full of amino acids, you know, the tronops, you know, life essential elements, and a whole bunch of other interesting molecules. So that's kind of delivery. There's also, you know, generating the substrates for life too. And this is an area that, again, I find fascinating, and, you know, learning more and reading origin of life literature myself is, you know, I think our increasing realization of the role of minerals in the origin of life. You know, that life used particular minerals as substrates. And one of the common things, and actually we chatted about this briefly at lunch with the grad students, is clays. And one particular clay, montmorillonite, keeps coming up because of it. You know, it has this unique structure. There's a lot of variability in the montmorillonite structure. You can put different things into that structure. So it's been shown, you know, through experiments that montmorillonite is able to catalyze a variety of organic reactions and, you know, participate in the formation of RNA. And, you know, when we go to the Reese crater, actually this particular thin section, which is about 3 centimeters across, is from Popogai in Russia. You know, we generate these impactites, these impact breccias, very heterogeneous products that in this particular instance, you know, we have all of the green is clay and all of the black is glass. So, you know, I don't have a slide on this, but, you know, the other thing that impacts do is, you know, bring together, you take, you know, a cross section through a planetary crust, you excavate it, mix it all up, you know, and then redeposited it together and then pump fluids through it. And you've got, you know, a lot of really highly reactive substrates and what's the word I'm trying to look for, you know, gradients, geochemical gradients happening on a very small time scales. And, you know, this 3 by 3 centimeter image shows you that you have, you know, reactive glass substrates and reactive clays present there. And again, the reese crater also shows us that, you know, these are ejector deposits from the reese. This is about 5 meters high here. There's a couple of layers of ejector, but the point here is that all of this greenish looking rock are these melt bearing breccias or swavite, for those of you who've been to the reese, that are the ejector deposits. Okay, so to kind of start wrapping up, and then I'll wildly speculate from Mars at the end. You know, to bring this back for this review paper that we did a little while ago, kind of drew up and wanted to start thinking of impacts in, you know, a slightly different way. You know, if I teach impacts in a purely in a geology class, we typically think of 3 main stages of crater formation: contact, compression, excavation, modification, and that's all over in, you know, a few minutes for all but the biggest basin size impacts. But if we think about a geological perspective, what we did in this paper was split it up into 3 kind of different stages: the thermobaric phase, hydrothermal, and then the succession phase. And so the thermobaric phase, you know, high pressure temperature is typically what we think about. You know, quite a hot, you'd think, you know, an environment that is not conducive for life. But you're already then generating really quite unique habitats. These, you know, highly vesicular melts, the glasses starting to form early clays, and you've got all of this fracturing going on. It scales with the impact depending on how quickly the next phase will occur. But, you know, on any planetary objects, and you could speculate, you know, on hydrous asteroids, on, you know, ice moons of the outer solar system where we never had any volcanic activity, on objects, you know, exoplanets, where you didn't have much tectonism or volcanism, you're still likely to have impacts. And, you know, even on Mars today, if you have a big enough impact, you will generate a hydrothermal system. Let's say if it was into mid latitudes where we know there was ground ice. It might be short-lived because it's a cold environment, but you can, you know, melt ice, or if you have groundwater around, you know, precipitation or seawater, you'll generate this hydrothermal pulse. And the other, you know, neat thing about impacts too is that you got both subaqueous and subaerial settings for these hydrothermal environments. And you know, from the literature, this, you know, not something I look at, but I think a lot of folks, and I would throw this question out to people in the room too, right? And I was talking with Steve Ruff earlier that the idea of subaerial hydrothermal environments where we have, you know, wetting and drying cycles are being thought of increasingly as perhaps more likely, you know, or more conducive environment for the origin of life than a permanently underwater hydrothermal environment. So, you know, you've got basically both in an impact environment. You know, after that hydrothermal pulse is done, we enter this succession phase. And, you know, this is important for biosignature preservation, but, you know, this can continue for millions or even billions of years. And so, you know, think of this where you've still got habitats that are unique because of the impact. And the Horton crater in Devon Island is a great example where these endolithic communities only exist in the impact crater environment and not, you know, 10 kilometers outside. So the Horton crater on present day Devon Island that is a polar desert is an oasis today. You know, eventually the whole environment on Devon Island will kind of equalize, but even 30 million years after the impact, the crater is a unique habitat for life. So, you know, if we go back to early Earth and early Mars and start to think again about, you know, origin of life, you know, I think, you know, at some point, both planets were, you know, maybe similar, quite similar early on. They, of course, took different paths, but in the Haitian, you know, we think early Mars had a big water budget. We had volcanism happening, but also, you know, roughly speaking, likely the same cratering rates that were occurring here on Earth. This, of course, is a location very familiar to people in this room, around the Isidis Basin. But I'd like to put up this version from a paper that Livio Tornabene, who's in my group at Western, published quite a long time ago, which is, the occurrences of hydrated silicates, mostly clays, concentrated in the heavily cratered southern highlands. And, it's easy, of course, to draw circles, right? To draw dashed lines. But, we don't know, I think, the complete story of the origin of clays on Mars. It is complicated. And of course, we're talking about this earlier too. But, a lot of these clay occurrences, these all fit within what would have been the Isidis ejector blanket. So if you took the Reese crater in Germany, scaled it up to Isidis, that crater would have thrown out ejector hundreds of meters thick, coming definitely out to this dashed line. And if we had enough fluids around, it would have generated hydrothermal fluid flow, potentially well out to that type of location. Nearly Fosse, we think, is a big fracture network, fault network connected to Isidis as well, that also could have been a big zone for focusing fluid flow. And so, maybe even though some of these craters are excavating pre-impact clays for these smaller craters, maybe they're excavating stuff generated through the Isidis ejector blanket. So, I do think, I hope this is something that, we think about more in terms of clays on Mars. It is complicated. If all you have is a remote sensing image and you see clays and a central uplift on Mars, how do you know whether that's pre-impact clays that existed before the impact that were uplifted versus ones that were formed by that impact? So it might be virtually impossible based on remote sensing data alone. But from future rover missions and some of the ongoing ones, maybe we'll get some answers there. Okay, to summarize and hopefully leave a few minutes for questions. So, hopefully I've shown you the impact cratering. It's common to all planetary bodies. And, in this case, I think I could speculate that it's common throughout the universe, based on our knowledge of how solar systems form. They can deliver the chemical ingredients for life and the conditions suitable for the emergence of life, both through substrates and habitats. And so, this idea that whether impacts helped create life and whether life originated in an impact crater, we may never know. But if that didn't happen, at the very least, you're creating, as life is originating elsewhere, all of these unique prime sites that are actually protective niches where life could then potentially thrive and evolve and survive that, first billion years of Earth's history, and potentially other objects too. And so with that, I will, I guess, super quickly, if you're interested in learning more about this, talks a bit of a snapshot from a review paper in Biology published last year. And I will, pause and take questions.
Thank you. Thanks very much. So we'll take questions from the audience here, and also if those online, if you want to ask a question that will be asked live, please put it in the Q&A.
What similarities, if any, do craters with evidence of hydrothermal deposits have in regards to their original impact events and conditions? So variables like pressures, temperatures, crater depth, etc., or even the environment like the soil composition.
Yeah, so the Reese crater and the Horton crater are probably the best examples. One's 23 kilometers across, one's 24. You could play around with variables in terms of differing impact velocity and impact the size, but the energy of those two impacts should be pretty much the same. So they're both also formed in similar-ish target rocks where you had sedimentary rocks overlying crystalline basement. So you would think that the Reese and the Horton crater should have evolved, fairly consistently the same. Starting conditions anyway should have been similar. So the major differences that we know of between the two is, obviously one was high Arctic Canada, but it was a lot more temperate 30 million years ago. One was southern Germany 15 million years ago. But I think it was that, rapid onset of quite a long-lived crater lake at the Reese that generated the more pervasive hydrothermal alteration there. So I'm not sure if that answered all of your questions, but yeah.
All right, we have a question online here. What work do you think needs to be done in the coming years in order to help answer some of the complex questions?
Oh, it's a big question itself, right? One question that may come up that I often get asked is, we don't have a very good understanding of the duration of impact-generated hydrothermal systems. Been discussing it with a few people today. Great area for the students out there wanting thesis projects. You know, I think we need to come at it from two angles. One is, you know, modeling this using computers. There's been a couple of people do this in the past, but not really any recent look at this. And then, you know, through better age dating. It's very difficult in small craters because, you know, because of your precision and accuracy of the hydrothermal setting for the age of the crater is going to overlap. But in bigger craters, you know, Sudbury, Chicxulub, and a few other ones, it would be good to get in there and really tease apart, you know, and age, you know, date different minerals, different parts of the crater to see if we can tease out the duration. So that's definitely one of the big questions.
Other questions in the room?
Hi, Oz.
Oh.
I really enjoy your presentation. That's awesome. So I have two questions. So in the introduction, you show the location of the impact crater on Earth. On the continents, it seems like they are clustered in the North American and kind of Europe. So have you considered to do some plate reconstruction? Maybe there is, what's the reason for that? And the second question is that, is there a possibility for that we have many impact craters on the ocean basins? I mean, on the oceans.
Yeah, no, great question. So I don't think constructed plates over time, you know, you've got to go back over a couple of billion years. I don't think that really plays too much of a role. What this is telling you is about the global geology. So, you know, you see a cluster in Australia, cluster in Scandinavia, and then kind of North America. And it's primarily because that's where you have, you know, these ancient cratons and shields. And so it's just that you've got older rocks, and so you've got a longer record to kind of build up that impact record. And that's definitely the major thing. It's definitely the case, though, that, you know, a lot of these blank spots are, you know, heavily vegetated. You know, how do you spot a potential crater in the Amazon rainforest? There's parts of the world where, you know, we don't want to go to, can't go to. And, you know, it's where geologists are active too. You know, I even look to, if you look at northern Canada compared to Scandinavia, you know, Sweden, it's a more accessible country, Sweden on the whole. And as they were, you know, actively mapping in, even in the 2000s, they almost doubled the number of craters that were found. But these were ones that you can't look at Google Earth and find them. They're ones that you can only do through kind of boots on the ground geological mapping. And so, you know, I think there must be a lot more craters in northern Canada still to discover. Ocean floor, absolutely. You know, that's where, you know, we have lost so much, right? Because, you know, there's what, 240-ish million years is the oldest part of the ocean floor. A lot of it's a lot younger than that. So we're constantly recycling the ocean floor. But then it also gets to the only dots on this map are confirmed craters. And still today, to do that, you need a sample in your hand to bring it into the lab to find evidence for shock metamorphism. So, you know, I've seen bathymetric images of things that must be impact craters, but we don't have any rocks from them. So, you know, proving them becomes very difficult. There's, you know, there's one dot in the middle there. There's some offshore continental shelf off the US, you know, and Chicxulub, of course, was a continental shelf impact. Some do remain offshore, but a lot, yeah, we're skewed towards looking for craters on land and ones that we can access. I may have forgotten part two, or maybe you didn't ask.
Yeah, thank you. That's all. Yeah, thanks.
All right, well, in the interest of time, I think we need to wrap up. So thank you very much again for a very nice, accessible talk. And thanks for coming all the way out here from Ontario to visit
Thank you.
us. Thanks.
And again, to those of you in the room, at least I'm around tomorrow as well. And so, yeah, happy to meet up if you've got other questions and want to chat tomorrow.